Well, hello everyone. We're continuing with section 6.3. Now we're going to look at a specific new type of problem. Suppose you want to find the other 5 trig ratios when you're only given one. So suppose you're told that the sine of theta is 3/19 or cosine of theta is -3/4 or something. How do you, only using that one piece of information, and you need to know also what quadrant the angle is in, because it may or may not be positive or negative. We need to know that. How do you do that? How do you solve that problem? Well, we're going to return and look at this following picture. So imagine that you had your usual axes, and I've put some reference angles on them, and you had a general point, we'll call it xy. And in this case it's in the first quadrant, but it doesn't need to be. But from its position you can see that this distance here is x, this vertical distance is y, and this distance, which essentially is hypotenuse, is r. Now from this angle, theta's perspective, won't x be called the adjacent, y will be called the opposite, and r, which if you think about it is just the third side of a right angled triangle, and therefore if you know x and y, can't you get r? Using Pythagoras, it would be the square root of x squared plus y squared. So if you know the point xy, then you can realise that x could be used to represent the adjacent, and y could be used to represent the opposite, and r could be representing the hypotenuse, as you can see here. Now, how does that help us? Well, if we then go and we look back at SOHCAHTOA, remember the sine is opposite hypotenuse, the cosine is adjacent over hypotenuse, and the tangent is opposite over adjacent. We can use that information and we can create this new set of formula for calculating what the 6 trig ratios are. And you notice that all these formulas just use the x, the y coordinate, or the value of r. Now, provided you know which quadrant it's in, and essentially all the quadrant does is tell you whether the answer is a positive or a negative number, you are pretty much good to go. So let's put this and apply it and see how it would work in practice. So the first example I'm going to look at here is coming up. Here we go. Find the other 5 missing trig ratios when you're told that the sine of theta is 3/5 and that theta is in the second quadrant. Okay, since we're told the angle theta is in the second quadrant, that means the sine and its reciprocal cosecant of theta are positive, and the other 4 trig ratios are therefore negative. So that, knowing it's in quadrant 2, tells us which ones are positive, which ones are negative. Now let's go back and look at the sine of 3/5. Well, we know that that's the y coordinate over r. So what you've essentially told us there is the information that y is 3 and r is 5. And that allows us to use Pythagoras. And we find out that in that particular question, the corresponding x value is 4th. Now once you know x, y, and r, you are pretty much plug and chug. The sine of theta is y over r is 3/5. Its reciprocal, the cosecant, is 5/3. Both positive. Why positive? Because theta is in the second quadrant. Had to pause there for a minute. Now the cosine is x over r, which is -4/5, and its reciprocal secant theta is -5/4. And the tangent is y over x is -3/4, and the cotangent is -4/3. So can you see that by the combinations of x, y's, and r's, we get all 6 trig ratios? And our starting information was really just 2 things. You told us what the sine of theta was, and you told us what quadrant theta was in. And that is pretty much the package. Put it together. Tell me one trig ratio and what quadrant that angle is in, and I'll be able to tell you, and hopefully so will you, what all 6 trig ratios would be equal to in that particular situation. Okay, this one. Let's see what it looks like. Example 2. We're being asked to again find the 5 missing trig ratios. This time you're telling me the cosine is 5/13 and that the sine of theta is less than 0. So these two guys here, knowing the cosine and knowing that the sine of theta is less than 0, you put them together and you should be able to get what quadrant theta is in. Well, since the cosine is a positive number 5/13, doesn't that make the angles where theta has to live the first quadrant or the fourth? And since the sine of theta is negative, and it's only negative in the third and fourth, the only place where both of those things are true is in our fourth quadrant. So, solved a little puzzle there. We now know it's the fourth quadrant, which tells me that the cosine and the secant, that's its reciprocal, are positive and the other guys are negative. Now we return back to the information that they gave us, where they told us what the cosine of theta was in its 5/13. Well, cosine is x over r, so indirectly you've told me x is 5 and r is 13. And now we can find, or use that information to find that y is 12. And then as I scan through these, you can certainly pause this video once we get to the bottom here and just for a moment look at where all these answers come from. Can you see the sine and its reciprocal cosecant? You see the cosine and its reciprocal, and finally the tangent and its reciprocal, the cotangent. You see the 4 guys that are negative and the 2 that are positive? Can you see the combinations of x, y, and r that generate the particular trig ratio that you're interested in? Well, let's have one more example of this. This is example 3 coming up now. Pretty standard question. Find the other 5 trig ratios when you're told 1. In this case, you're being told the cosecant is 3/2 and that the tangent is less than 0. Now, since you're told the cosecant is 3/2, that also means that the sine then is 2/3. And in these kind of questions where the guy that they tell you is one of the reciprocals, the secant, the cosecant, or the tangent, it's useful to take that information and immediately convert it into sine, cosine, or tangent, in this case the sine. Now it is positive, and the tangent is negative. And if you go through all the places where that happens, it ends up being that the second quadrant is the only place where angle theta can live, which means that the sine is positive and, of course, the cosecant is positive, but the other 4 are negative. So, if the cosecant is 3/2, can you see why the sine is 2/3, right? The reciprocals of each other, which is essentially telling us the x's and the y's, or as I've labelled them here, adjacent hypotenuse, but isn't the adjacent the x, and the opposite is the y, and the hypotenuse is r. So you put those guys together. And can you see the working for the sine, the cosine, and the tangent? And can you notice that the 4 that are negative are the cosine, secant, tan, and cotangent combinations? The next little section is called the odd and even properties of the trig function. What these essentially tell you is that if you find the sine of an angle, let's say negative pi upon 2, it has the same value as the sine of pi upon 2. The only difference is that it may or may not be the same sine. So let's see what that means. For instance, the sine of negative theta is the negative of the sine of theta. So the sine of negative pi upon 2 is negative the sine of pi upon 2, for example. Now, sines and cosecants have the same relationship, that they are negatives, and these are called odd functions. And the tangent has that same property, that the tangent of a negative angle is the negative of the tangent of that angle. So sines, cosecants, tangents, and cotangents are all odd properties. And the two guys in the middle, let's move this down a little bit for you. The cosine of negative theta is the cosine of theta, and the secant of negative theta is the secant of negative theta. Those are called even functions. So there is a property that says that if you take the say the trig function, the cosine of a negative, and it's still the cosine, when the signs are the same, plus is always plus, you are looking at an even function, whereas the sign of these changes the sign of the answer, and these are called odd functions. So how could you use that? Well, you can use it to find examples of exact values for some trig functions like the sine of negative 120. Now, there are other ways of doing this. I mean, we could simply just find out what angle's the same thing as negative 120, which happens to be positive 240, and then use a unit circle. But in this case, can't we use the property that it's the negative of the sine of 120, and then look that fella up, the sine of 120, and you'll get root 3 over 2, and then stick a negative in front of it. So it can be a little bit quicker, more convenient. What about cosine of negative 5 quarters? Well, it's the same as just a normal cosine of positive 5 quarters. And if you look that up in the unit circle, it's root 2 over 2. And what about the tangent of, say, something like negative 300? Well, it's the negative of the tangent of 300. Now you look up the tangent of 300 and it's a negative root 3. So it's a negative of this guy, so it ends up being positive root 3. Now for the last examples we're going to look at here, we're just going to do some of the slightly more awkward versions. Suppose you wanted to use the odd even property to get the exact value of the cosecant of negative 3 upon 2 pi. Well, the cosecant of a negative angle is the negative of its cosecant. So the cosecant of this fella is negative 1 over the sine of this fella. Right? The sine of this fella is negative 1. Calculate that, and the two negatives cancel out, and you get 1. And for the last one, how about the secant of negative pi upon 4? Well, since secant of negative theta is the same as the secant of theta, which is 1 over cosine, the secant of this fella is negative 1 over the cosine of this guy, which is negative 1 over a rather awkward root 2 over 2, but if you do its reciprocal and then rationalise the denominator, you finally get that. And that is us, so we are finished.